In this session, we're going to talk about chemical kinetics. Now, what are some of the things that you're supposed to understand on this topic? So we're going to talk about all the concepts that are here. We're going to talk about units of rate, rate laws, all these concepts. We're talking about them. Then after this, we're going to solve some practice questions or exam questions. So these are the questions and we're going to solve all of them. Now, I would implore you that when you start solving these questions, you can be pausing the video, you try. So that's how you familiarize yourself with the concepts. Okay. So basically, what is, chemical kinetics? What do we mean when we say chemical kinetics? Now, one thing that you should understand is that when we're talking about kinetics, we're talking about motion. Okay, so and when we put the aspect of chemical here, we're talking about the chemical reaction. So we're trying to monitor the rate at which a reaction is moving. Okay, therefore chemical kinetics will just be a branch of that chemistry, or the branch of chemistry that will deal with the study of rates of reactions. It's going to deal with rate laws. It's going to do with reaction mechanisms. It is also going to do with catalysis. Catalysis has all to do with speeding a chemical reaction. So in chemical kinetics, what are you supposed to understand? You are supposed to understand the rate. Okay, now the rate is the time. Okay, now the rate of a reaction, okay, the rate of a reaction, the way we're going to find the rate of the reaction, typically it will just be expressed as a change in concentration over the over a specific period of time. Okay, so if this is the rate, this concentration that we're talking about is the concentration of the either the products or the reactants, okay, over a specific period of time. Now, what will be the units? We know that concentration itself is measured in moles per liter, or molar, like that. Over time, we know that it is measured in seconds, which I'll put as S. Therefore, the units for a rate of a reaction, we're just going to have mole per liter second. Okay, so basically that's what you're going to have, or you're going to just have molar per second. Okay, so this is very, very important for us to understand. Now, this rate of reaction is affected by several factors, and you're supposed to understand those factors. First and foremost, what can affect the rate of a reaction? It is the concentration of the reactants. So how do the reactants affect the rate of a chemical reaction? So let's imagine you've increased the concentration of the reactant. So when you increase the concentration of the reactants, what will happen is the rate of the reaction is going to also increase. Why? Because now you have more particles that are able to collide. Okay, basically that is the basic premise on the concentration of the reactants. Okay, then temperature can also affect the rate of a reaction, which we are going to see when we start talking about what we call the ARHHENIUS equation. So now the temperature itself, what you should understand is that the higher the temperature, or higher temperatures themselves, what higher temperatures do is that they generally increase the rate of the reaction. How? As the particles gain more kinetic energy due to higher temperatures, you're going to have more collisions. Okay, because they have a lot of kinetic, they are moving at a higher rate. Because of that, you have a lot of collisions between them. So temperature also increases the rate of a reaction. Then thirdly, you can also talk about the surface area. Now on this one, if I have a stone, or let me just say something that is in a solid form, and I've just put it in a solution, let's say I put it in water and that I leave it to react, this might take, even forever, or it depends with the type of a solid, but at the end of the day it will be a very slow reaction. But now just imagine I crush this stone into smaller pieces. By doing this, it means I've increased the surface area. Each of the particles, even the ones here, because the ones that are inside, for us to reach what is in the middle for the stone, it will be very hard. Okay, but when we crush it, now almost all the particles can now react in the reaction. So because we've increased the surface area, we have a lot of particles. In this case, they will be exposed to react, and because they're exposed to react, that will also speed up the reaction itself. So that is very important for us to also understand that surface area also affects the rate of the reaction. Then we can also talk about a catalyst. Okay, so basically you're going to have metal catalyst, biological catalyst, and other forms of catalyst. Basically, when you add the catalyst, it just speeds up the rate of a chemical reaction without itself being consumed in the process. So how does it do this? It does that by lowering the activation energy, which we are going to talk about. Because before any reaction happens, this activation energy barrier has to be, it's a barrier actually for a reaction to occur. So when you overcome that barrier, that's the only time that the reaction is going to occur. So what a catalyst does is that it lowers that barrier so that the reaction happens faster. Okay, now this kind of catalyst, there are different kinds of catalysts that you can talk about. You can have a homogeneous catalyst. Now homo to mean is the same. You can also have a heterogeneous. Now homo, in this case, the same in that regard, we're talking about in the same phase. Okay, it is in the same phase as the reactants. So let's say the phases, the phases will go solid, liquid, gas. If your reactants, or let me say, are in aqueous, then your catalyst is also in aqueous. It means that catalyst is homogeneous. Okay, it's able to combine without you even able to see it. Okay, however, if your reactants are maybe in a liquid, or let me just say they are in a solid, then you've put that solid in maybe your catalyst is a liquid. Probably they are in different phases, so that is called the heterogeneous. However, they are just going to work the same, whether homogeneous or heterogeneous. It's just speeding the reaction. Then another kind of a catalyst that you can have is an enzymatic. Okay, or an enzyme itself. Now in this case we're talking about biological catalysts. These ones are non-metallic, so these ones are going to catalyze specific reactions. In your body you've got an enzyme that is involved for carbohydrates, an enzyme that is involved for breaking proteins, and all those things. These ones are specific and they are biological in nature. Actually they are proteins, that's what we can just say. So basically these are just some of the things that you're supposed to understand. Now what are you also supposed to know here? I've talked about a catalyst. So let's say this is our energy profile diagram. This one is our energy, okay, the change in energy. Then let's say this is the reaction progress. Okay, this is how our reaction is progressing. So you're going to have your reactants, and they're going to move like that and form the products. You're going to have another reaction. Okay, so basically you've got these two reactions. So this is the energy barrier that you need to overcome for the reaction to occur. Then this one is for the second one. Okay, so able to see that this the second one, let's say it is an uncatalyzed. Okay, and catalyzed pathway. The other one, this one, to be catalyzed. Okay, so to be catalyzed in the essence that the reaction is happening faster. The second reaction for the catalyzed one is happening at a faster rate compared to the previous one. Okay, so that is also very important for us to understand. That's what the catalyst does. It lowers that activation energy, that barrier. Okay, now when you're finding the rate, there's what we call the average rate, okay, and the instantaneous. Now when you're finding the average rate, you're trying to find the average between the two, 2 points. So we're saying rate is equals to the concentration over the time, right? But now this concentration, you're going to have an initial concentration when the reaction is starting and the final concentration. So you're going to subtract the final concentration, which I'll just abbreviate as C2, minus the initial concentration. Okay, now the way we denote concentrations, we put in these square brackets to mean that this is the concentration and the other one is the concentration. Okay, basically this is what you're going to have as your concentration. And then you're going to have the initial time and the final time. So you're going to subtract the final time, which I'll call as T2 minus T1. Basically this is how you're going to find your average rate. Now what you're able to see is, if let me say the concentration that I started with was a 2 molar, or let me say it was 10 molar, then after maybe a certain period of time, let me say after maybe 20 seconds, now the concentration finally, it is like of the reactants, let's say it is now 2 molar. Okay, now the time, let's say we're saying is 20 seconds. So let's say initially we know that it started from let's say maybe 1 second, then finally it was like at 20 seconds. You're just getting the final minus you're getting the final, the final minus the initial. Yours for time the same one, the final minus the initial, and you find your average. Basically that's what you're going to do, and this is what we have just shown here. However, when you're talking about the instantaneous, it's a bit different. You just don't want to find this whole range from 2 to 10 and from 20 to 1. No, you can find at a specific point. Let's say you want to find the rate at maybe, let me say at 11.5 seconds. You're going to use the instantaneous rate equation, and the way you're going to find that, it is going to be, you're going to differentiate the concentration and differentiate the time. Okay, dc dt. Now this is with respect with what you've been given. So basically this is how you're going to find your instantaneous rate. Okay, and that is very important for us to understand. Okay, now that we've talked about that, you also have to understand what we call theories of chemical kinetics. So what are some of these theories that you're supposed to understand? Number one is the collisions theory. So according to the collisions theory, molecules must first collide. Okay, they must collide with a lot of energy, or let me just say sufficient energy, in order for a reaction to occur. Okay, otherwise there will be no reaction. Okay, then another theory that you are supposed to understand is what we call the transition state theory. So what does this theory state? So a transition state is just an unstable state of reaction. So before your reactants convert to products, they have to first reach at a very, very high energy. Okay, now that high energy is just a very short-lived kind of a state where you have a mixture. If let me say you're converting a solid to a liquid. Okay, the transition state for this one, it will be a mixture of a solid and a liquid. Okay, that will be the transition, and it's just short-lived. Where you have a mixture, then you go direct to your products, which is the liquid. So that is a transition state. It is just in between, and it's just short-lived. It's not for a long period of time before you go to your products. So what do I mean here? Maybe I can explain this in terms of a diagram. Let's say this is our energy profile diagram. Okay, now, and these are reactants, then they go and give us the products. Okay, so let's say what is reacting. We have A is reacting with B, C. Okay, now let's say A is displacing B, okay, or is displacing C, then we just remain with AB. So our product, we are saying we are going to have AB plus C. Those ones will be our product. And this barrier here that we are overcoming, this barrier that we are overcoming here for the reaction to start from here to there, it is that we are calling as the activation energy. Okay, now at this topmost point, that's where we have the transition state. That's where we are going to have the mixture. Now that mixture, what is going to happen is that it's like one part is breaking and the other one is being formed. Okay, so the way I'm going to represent it is A is forming a certain bond with B, then B at the same time it is breaking away from C. So this will be a transition state, and that's how you're going to show it. Basically that is what you're supposed to understand. Then on this topic, you're also supposed to understand what we call the rate law. Okay, so the rate law, you're going to get the rate. In this case, it is multiplied by, how are you going to find the rate? It is the rate constant, which is K, multiplied by, let's say I have a reaction, you have the reaction which gave you A and B as a, so what you're going to have, you're going to have A, the concentration of A to the power M, and the concentration, let's say M, then let's say you have B, the concentration of B to the power N. Okay, basically this is how you're going to find your rate. So what are you now supposed to understand? The rate constant itself, the K that you are seeing, it just relates the reaction to the concentration. How do I mean? Because that this is the concentration, okay, of the reactants. Okay, so basically if I'm going to find the constant, I'm just going to divide by the concentration on both sides, right? Therefore I'm going to find my K as the the rate divided by the rate of this reaction divided by the concentration. Okay, the concentration in case it is concentration of the reactants. So basically that's how you're going to find your rate like that, and that is very, very important for us to also understand that. Now I have to mention something here. Let's say you have the reactant A. Reactant A gives you a product. Okay, now when it's just like that, it's just alone as a reactant, the rate is going to be your rate constant multiplied by the concentration of A as a reactant. Then let's say now with double A, we say now we have 2A. 2A gives us a product. Okay, now what is going to be the rate? The rate in this case is going to be K, the rate constant, multiplied by the concentration of A squared. Why? Because we've doubled A. Now let's say now we have two reactants, not just A. We've not doubled A itself, but let's say we've got A. In this case we've got with B, and these ones give us a product. So what is going to be your rate? So the rate in this case, it's going to be the rate constant multiplied by the concentration of A multiplied by the concentration of B. That's how you're going to find your rate. However, let's say now we want to, maybe let's put 2A here plus B. What are you going to have? They give us the products. Okay, what is going to be your rate? So your rate in this case is just going to be your rate constant, which is K, multiplied by A. Since A is doubled, I'm going to put squared multiplied by B. Basically, these are just some of the, the principles that they're going to give you. They're going to give you diagrams to see if A has been doubled, which one are you going to use? To see if B has been doubled, which one are you going to use? Okay, basically these are some of the principles that you're supposed to understand. Okay, now let's talk about order of reactions. So order of reactions, there's what we call a first order of a reaction, there's what we call a second order of a reaction, there's also what we call a zero order reaction. So basically, what are we talking about here? What is the first order reaction? So the first order reaction is the one that we just talked about initially. We said rate is equals to K multiplied by the concentration of A. Where you have A as a reactant, it gives you a product. Okay, basically this is the first order reaction. Now what will be the units of this reaction? Because it's very, very important. Now we said rate is measured in mole per liter second. Okay, this will be equals to K is a constant multiplied by the concentration of A. Now concentration, we said it is measured in mole per liter. Okay, so for me to remain with my K in this case, the rate constant, I'm going to divide by mole per liter on both sides. Even this side, mole per liter. What will be my K? Okay, so now we're able to see that if I'm going to write it nicely, okay, I've got on top, I've got mole per liter. This is multiplying by a second. Okay, multiply, this is dividing, so if they are dividing, I'm dividing by mole per liter. Now because I'm dividing, what am I going to have? Because I'm dividing, it means this one becomes the numerator, this one becomes the denominator. So let's write it like that. So it means I'm going to have liter on top, then mole down. Now that I've got this, what is going to happen is that the mole and the mole are going to cancel. The liter and the liter are going to cancel. Okay, now what I have on top is, or when I had to shift this one, you know that the symbol also changes, right? So it means this one is 1, this one is 1. Okay, and we just remained 1 over S. We've remained with 1 over S as our answer. So that is the unit. But now this 1 over S, you know that if I've got 1 over 2, can also, in terms of exponentials, it's the same as 2 to the power negative 1, right? So even in this case, that's what we're going to write. It's just the same as S to the power negative 1. So this means per second. Okay, therefore the rate constant, the constant of a first order reaction, the units will just be per second. So anytime you see a constant, a rate constant with per second, that is a first order reaction. Okay, even before you solve. Okay, basically that's what you're supposed to know. Okay, now that we've talked about the first order reaction, what about the second order reaction? So the way we're going to find about the second order reaction, we said you have rate will be equals to K multiplied by A. In this case, A can be squared. Okay, a scenario where we had 2A as a product, it gives us a product. Okay, we said because there are 2, you are going to double it. Okay, so basically this is how you're going to solve it. Now we've got 2, you can also have 2 reactants, so the rate of a second order reaction, it can also be written as K. Let's say you have A, like in that case where we had A and B, so it can also be written like that. and that is very, very important for us to understand. So that's how we're going to find for a second order reaction. Now, what are the units, okay, for this reaction? Let me just use this one for the one that is only 1 as a product. Okay, so for this one we're saying rate. Let me make K the subject of the formula in advance, because I want to make K the subject of the formula. I'm going to divide by A squared on both sides, the concentration of A on both sides, and is squared. So these ones are going to cancel. Therefore my K is just equals to the rate over the concentration of A squared. Okay, now if that is what I have, what is rate? Rate, we said we measure it in mole per liter second. Okay, this is dividing by the concentration of A, that is squared. Okay, now the concentration, we said it is measured in mole per liter, right? If that is the concentration, now this is squared. Okay, now if it is squared, it means mole is going to be squared and the liter is going to be squared. Okay, so therefore that's what I'm going to write. I'm going to write mole squared over liter squared. Now if I simplify this, I'm going to have mole over liter second. The division symbol changes to multiplication. I'm going to have liter squared on top over mole squared down. Okay, now if this is what I have, I can now divide. Okay, so the liter and the liter are going to cancel. Here I'm going to remain with 1. Okay, the mole, 1 more here will cancel, the other one more. I'm going to remain with 1 more here. Okay, so what do I have? You're able to see that now on top, if I multiply with what I have on top here, this is a 1 multiplied by liter, 1 liter actually, because one of them has gone, right? So I'm just going to remain with a liter on top, divided. Here I've remained with an S. I'm going to write it S. This S is multiplying by a mole. I'm going to write my mole. Okay, basically these are the units. For maybe to simplify it further or to write it nicely, I'm going to say this is the same as a liter per, because the division symbol means per mole second. When I put a dot, it means mole and second are multiplying just the way they are down here. Okay, basically this is the units. These are the units for a rate constant of a second order reaction. So anytime you see liter per mole second, you just know that okay, this one is a second order reaction because the constant has given you that. Now what about a zero order reaction? Now for a zero order reaction, rate is equals to K. Okay, so what are you supposed to understand on the zero order reaction? You're able to see that if it is only equals to K, rate itself is independent of the reactant. So it means that it doesn't depend for this kind of a reaction, for it to move or for it to maybe even just how fast this reaction goes. It has nothing to do with the reactants. So what do I mean? If I've got A plus, let me say, B, that is just giving me maybe, let me say, AB. Okay, so if I'm going to put the constant K AB, so this is a constant. So if this reaction was a zero order reaction, so if I doubled A, even if I said I put a 2 here, nothing will happen here because the reactants have got nothing to do with the rate constant. Even if I added a 2 on B here, well, even if we know that we're supposed to square B, but we're not going to do that. Why? Because it's a zero order reaction. It is not affected by the reactant. Whatever you're going to do with the reactant, whether you double them, you half them, it has nothing. So such kind of a reaction, even if they show you on a table and you're able to see that okay, in reaction A, the rate hasn't been doubled or nothing has happened after maybe even doubling the reactants, that will be a zero order reaction. It is not affected by the concentration of the reactants. Now let's come up with our rate. Now we know that rate, and let's make K the side of the formula. K in this case is already the side of the formula. Now how did we say we measure the rate? We know we said the rate, you're getting the concentration, and concentration is measured in mole per liter. Okay, mole per liter. This liter is multiplying by seconds because you're doing more the concentration over time. So it will be more per liter second. Okay, this will be equals to K. Okay, so basically this is what you're supposed to understand. However, some literature are going to say this is the same as molar, because we know that molar per liter is molar, so molar per second. Okay, once you just see such kind of expressions in terms of the rate constant, that is a zero order reaction. So that is very important for us to understand. Now we've talked about concentration with respect to time in terms of orders. What about laws? They are what we call integrated laws. Okay, so for integrated laws, what are you trying to do? So you are trying to, in simpler terms, you want to compare the concentration to time. Now people have come up with equations to explain that, and that's why they are called laws. So basically these are concentration to time equations. That's what I can just say. Okay, so now what are you supposed to understand about integrated rate laws? Okay, let's start with the let's start with the first one. What if you are talking about the first order reaction, then a second order reaction, then a zero order reaction? So what is the integrated law for a first order reaction? So it is the natural log of A over the natural log, okay, it's just like that, initially multiplied by T. This is equals to negative KT. Then when we come to the second order, it is 1 over the concentration, let's say A in this case, multiplied by T. This will be equals to 1 over the concentration of A initially plus KT. Then we come to a zero order reaction. For a zero order reaction, the concentration of A is equals to negative KT plus the concentration of A initially. So these are the integrated rate laws. Then I think it is also very important to also talk about the half-life. Let's say, yes, you want to find the concentration in relation to time, but what if you want to find it halfway, okay, after the reaction has happened? You're just trying to, okay, halfway, what will remain, okay, in terms of the concentration, so, or at a certain time. So T half, which is half-life, will be equals to, for the first order reaction, for a first order reaction, the way I find your T half is equals to the concentration of A over 2K. Okay, then the T half of a second order reaction is going to be natural log of 2 over K. Then for a zero order reaction, the T half, or the half-life, will be equals to natural log of 2 over, it's going to be not really natural log, it's going to be 1 over K multiplied by the initial concentration of A. Are you supposed to know the T half? Of course you are supposed to know them, because they can ask you halfway what will be the that you have. Okay, so that is very, very important for us to know. Now you can either master them, you can also know them by deriving them. Now let's just derive them in case maybe you forget about them. Okay, now a zero order reaction, what did we say the formula is? We said the rate, it is not affected by the reactance, so rate in this case is equals to K, just K itself, the constant. Since rate is equals to K, okay, and you know that rate, it will be the concentration, let's say in this case the concentration of A over time, okay, with a specific time. Okay, now you know that this rate, because time should not be negative, I'm going to put rate should not be time. Okay, it doesn't make sense if you say this reaction took about -5 seconds to complete, so I'm going to put a negative in front so that in case we have a negative when we solve, it's just going to cancel itself out. Okay, now what I'm going to now have is I'm going to differentiate this. When I differentiate, I'm going to have d a dt. Okay, so that is the rate. If this is the rate, this rate is also equals to K. Okay, so K is also equals to that. Okay, so what are we now going to have? So I'm going to have my K now. We are always concentrating on K. K will be equals to, because we're saying it is the same as so it will be the same as the rate, which is that over dt, after we've differentiated. Okay, now after we've differentiated, what is going to now happen? I want to put A on its own. So because I want to put A on its own, I'm going to have negative D is equals to K multiplied by dt. Okay, let's say now we've differentiated, I'm just going to have negative of A is equals to, okay, just for me to remove the negative, I'm going to divide by the negative on both sides. Okay, when I divide the negative on both sides, I'm just going to have my concentration of A will be equals to negative K T. We've differentiated now. Now that we've differentiated, I'm now supposed to integrate. Okay, integration. So when I integrate the concentration of A, I'm going to have the concentration that I'll get for A, that will be equals to, now for this one, when I integrate it as well, it's going to just be negative KT. Okay, now whenever you're integrating, you're always adding A plus C. This is a constant. Okay, so I'm also going to add A plus C. Now what is this C in this case? So you know that C is a constant of integration at T is equals to 0. Now at T is equals to 0, that's when the reaction is starting. Okay, so what is the concentration of A at T is equals to 0? That is what we are calling the initial concentration. Okay, so it means C initially it will just be the concentration of A, because that's when it's just starting. Okay, so therefore where there is C, I'm going to also put the initial concentration of A. This is the equation that you are supposed to master. Okay, or that you are supposed to know on a zero order reaction. Okay, so this will be applying to all of them. Let's come to a first order reaction. So for first order, we said it is rate, where I just have A alone, so it is going to be K multiplied by you only have a single product, a single reactant. So since we've said the rate is equals to, we've said you're getting the concentration of A in this case over time, right? Now you're going to differentiate this one. We've said it's not supposed to, the rate should not be supposed to be a negative, so I'm putting a negative in advance. So that is what is going to, that's what we're going to have on rate. So on rate, I'm going to put negative D concentration of A over dt. This is equals to K multiplied by the concentration of A. Okay, now that is what I have. So now that I've got this, I'm going to integrate on both sides. Okay, don't forget that you're also differentiating. So what are we going to have? Now that we've differentiated that, let's now integrate on both sides. Okay, so when I integrate, what am I going to have? Okay, first let me make the subdivision formula like we did in the previous one. I had to put negative a as a concentration. This will be equals to, when I multiply it to be k multiplied by the concentration of a d t. Okay, now I'm not going to put the d now for now, because I assume we've already differentiated. So I'm just going to put t. What am I putting in this case? I'm just going to put t. Okay, that is what I have. Now if that is what I have, I want a and a to be alone, so I'm going to divide first by the negative on both sides, right? When I divide on both sides on the negative, okay, so this negative that we have on a is going to go, but it's going to come on the other side. Okay, now if that is what I have, I'm now going to divide by the concentration of a on both sides, because I want to have the a's on the same side. So these ones are going to cancel. Okay, now that I've got this, what do I now do? I'm going to introduce natural log. Okay, so I'm going to have the natural log of the concentration of a. Okay, let me just use a different color. In this case, I'm going to have the natural log of the concentration of a over the concentration of a. Now this one is initially, this will be equals to negative k t. Okay, negative k t. Then you have to remember that I didn't just show also that we're supposed to integrate, because you are integrating. Okay, after you differentiate, you're always integrating. So because you are integrating, you're going to put a plus c. Now what is the c Kaylee here? So the c in this case is a constant of integration, just like the previous one. And you know that at initially, you know that when you're starting a reaction, time is goes to 0. Now what will be the concentration of a when time is goes to 0? It will just be the initial concentration, right? And that's what will be our c. But now in this case, there is a natural log here. So in this case, it is the natural log of a initially. Okay, so basically that's what we are going to have, because that's the concentration of a initially. So in this case, I'm going to put natural log of a, but now this one is initially the initial one. Basically this is how we are going to find for a second order reaction. This is the formula that you are going to use. Okay, now what about a second order reaction? So about a second order reaction rate, we said since there are two reactants or we are doubling them, it is going to be k. Now let's say if it's a single reactant, then it is doubled. Okay, that is for a single reactant. Okay, now it's the one that I'm going to use to derive the equation, because it's the one that we use. Okay, for the one with two, it's a bit complicated. Okay, so in this case, what are we going to do? We're saying rate is the same as just the differentiation. You're differentiating the concentration of a over dt. Okay, this will be equals to k a squared, like that. So that is what you have. Then you're going to integrate on both sides. Okay, now when you integrate on both sides, what are you going to like have? So now I want the a's to be alone, like I did in the previous one. Okay, so you are going to realize that after I've differentiated and after I've integrated, okay, those ones are going to follow each other stepwise. Okay, let's say we've differentiated already and we've integrated already. So I'm going to have my a, the concentration of a, I'm going to be equals to the dt. I'm going to multiply with the other one. Okay, so I'm going to have I'm going to have k t. I'm going to remove the we've already differentiated. Then the a squared, because it was a squared, I'm going to divide it on both sides. And because here there's a negative, it was on a, so I'm going to divide it on both sides as well. So I'm going to have a negative here. Okay, then I'm going to divide by the a squared on both sides. This is what I have. I've divided on the other side, it has cancelled. Okay, now if this is what I have as that, what am I going to do? I'm going to now introduce the what can I do in this case? I can divide if I want, because here I've got a and here I've got a squared, so 1 is going to go, and when 1 goes, the one that is on top is going to go and divide. I'm just going to remain with a 1 on top, so it means on top I'm just going to remain with a 1 over the concentration of a down, because it was squared down. Okay, so that is what I have as like that. So if this is what I have, what now is supposed to be there? Now what, because we had to integrate, there's also a c, and what is that c? That c is the concentration of a when it was starting. Okay, so in this case, what is the concentration of a? It is 1 over the concentration of a. But now in this case, it is, you're talking about the initial one, initially when it was there. So basically this is the equation that I don't want you to forget. Okay, now of course people have come up with a lot of ways of how they derive these ones, and also, you know, several of, you know, how you can solve these ones. But basically these are some of the equations that you're supposed to know, and that's how you derive them. Very important. Now let's talk about the ARHHENIUS equation. Now, you know, ARHHENIUS is mostly known in, you know, for bases, acid base, you know, equilibrium, where you are defining acids and bases based on the number of hydroxide ions and the number of hydrogen ions. Okay, so like an acid would be that one with a lot of, you know, hydrogen ions in a solution, or hydronium ions, but a base will be the one with a lot of hydroxide ions. Now it also contributes to, you know, this topic of discussion today, which is chemical kinetics. So according to ARHHENIUS, you are trying to understand how temperature now affects, like I said initially, you're trying to understand how temperature affects your reaction rates. Okay, or the rate of a reaction. So how does temperature affect that? So we use the formula. So K is equals to, this is the ARHHENIUS equation, AE, okay, to the power negative EA, or activation energy, over RT. So this is one equation that you can use. However, you can also use another one. Okay, so natural log of K2 over K1. This is equals to EA over R 1 over T1, okay, minus 1 over T2. Basically these are the two equations that you are supposed to know. Now what are some of these things? What is K in this case? K, we know that it is a rate constant. Okay, it's a constant. Then A, from the first equation, A in this case we're talking about what we call the pre-exponential factor. So the pre-exponential factor, this one usually is related to the number of collisions. How frequently are your collisions? Okay, how frequent are your collisions? Then your EA, this one we're talking about the activation energy. Now I'm just going to talk about a bit about the activation energy, because it's also very important that you understand something. Okay, because the activation energy, it affects the reaction so much because it is the energy barrier for the reaction. Otherwise a reaction is not going to occur if the activation energy is not exceeded. Then R is a gas constant. Of course it's a constant they're going to give you. Okay, then temperature is just T, T1, T2, those ones are temperatures. Okay, so basically this is the these are the what the Arrhenius equation is. To simplify it in simple terms, the equation just shows that the rate constant K, okay, the rate constant K increases exponentially. You're able to see that it's an exponent of this exponentially with the time. Okay, because T with not time, with temperature actually. So basically that is it. Okay, exponentially with the temperature. Now I've talked about the activation energy. What are you supposed to understand about the activation energy? So the activation energy will be the minimum energy that will be required for a reaction to occur, or that energy that will be required for you to initiate. Okay, to initiate or for that reaction to occur, the activation energy has to be overcome. Okay, now the slowest step in any reaction is called the rate determining step. This is very important. Okay, it's called the rate determining step. Okay, that is very, very important for you to know. Now let's say we have a reaction A plus B. Let's say it is equals to C plus D. So this reaction, it can go either two ways. Okay, it can either be, it can start as A, just like this, A plus B as the reactants, then it goes like that and you form your products. Okay, or it can start from down, go like that, and it forms our products like that. Now what I've written here is very, very important. So this is A plus B, these are our reactants, then they formed our product C plus D. So for the second scenario, this is still A plus B, they formed our reactant C plus D. Okay, now what we have here now is from here to there, that is the barrier that this first reaction is trying to overcome. So let me call this one A, then this goes on 1, this one Roman numeral 2. So for the second reaction, this is the barrier it needs to overcome for it to start. Okay, then we said this topmost is what we are calling the transition state, right? Just to remind you, the transition state. Okay, however other books are going to refer it as the activated complex. There's a lot of energy, okay, and it's short-lived, like we said. So now these reactions that we have, what can we conclude about them? Let's say this is the potential energy, we have the energy on the other side, this is the energy profile, right? This side is the reaction progress, and this is the energy that you have. Okay, so what is that? Okay, so now that we've got this, what do I want to say? So what you're able to see is that the lower the activation energy, the faster the reaction is going to happen. Okay, so and the higher the activation energy, the slower the reaction is going to start. Okay, this one has to overcome all this barrier for it to start. Now what I've drawn here is something that is very common to some of us. The first one, this one is called an exothermic reaction. On the other side, on my right hand side, this one is an endothermic reaction. Now, why the difference? So an exothermic, we know that yes, it releases heat, but now why does it release heat? Is because bonds are being formed. There is bond formation. Okay, so it is very, very easy to form a bond. However, endothermic, bonds are being broken. Okay, so bonds breaking. Okay, so basically it doesn't really like equate to maybe normal scenarios of life where it is very easy to form a bond, but it is very hard to break a bond. But actually it is usually life is the opposite. You can easily make a bond with someone, right? But you can also easily break a bond with someone. Okay, so basically like that. So for reactions, it's like the opposite. It means for you to break a bond, a lot of energy has to go into breaking those bonds. Let me say this is A and T, like maybe let me say this is adenine and guanine, adenine and thymine, like in your DNA. You know that between them they only have 2 bonds. Then you've got guanine and cytosine. Between them you've got 3 bonds. Now for adenine and thymine, it will be a very, very simple process because it only has 2 bonds. But for this other one, more energy is also needed to also break the last bond. Okay, therefore for this other one it's going to take longer. Okay, basically that's what the premise is. It is very, because you're spending most of the energy to break those bonds. Okay, so this one is going to absorb energy, this other one is going to release energy as bonds are being formed. So basically that's what is an endothermic reaction.